Okay, we all good? All right, this is where we're going to get into something that's going to be new terminology, new concepts. When we describe how fast a reaction is going, normally we don't just measure the concentration over time. I mean, that's fundamentally what the rate is. We describe the rate of reaction with something we call a rate law. And a rate law is nothing more than just a description of how fast the reaction is. It's describing what factors are impacting the rate. So there's two types of rate law. And the two types are differential rate law and integrated rate law. And the difference between these two types of rate law is it just depends on what information you get. What is easier to measure? Is it easier to measure the concentration as it affects the rate? Or is it easier to measure the concentration, how it's changing over time? Differential and integrated. What does that sound like? Yeah. Sounds like calculus. Yeah. Now, if you haven't had calculus yet, and if you're watching this on YouTube, don't feel intimidated right now. You're not going to have to do any calculus. I'm not going to teach you any calculus in this. I will show you how we get the integrated rate law, and it's going to use calculus, but you're not going to have to do it yourself. It just kind of boils down to something that we can all deal with, regardless of where we've gotten to in math. So please don't go run and hide. Okay. Oops. All right. Now the bottom part of this has some things that are essential to understanding rate law. So the differential rate law and the integrated rate law, they look very different. They're both mathematical equations, but they don't look the same at all. However, they wind up giving the same information. It just depends on what you're given. What variables are easiest to measure is what determines which of the two types of rate law you're going to use. Now this middle of the three bullet points, this one right here. This one, I want you to put a star next to if you write it down. You can't tell anything about the rate of a reaction by doing anything except running the reaction and measuring how fast it's going. You have to determine the rate law by experiment. There's no way you can look at a chemical equation and determine anything about the rate law. Two labs. Yep. We have a reading quiz tomorrow. Don't forget about that. The reading quiz is the reading assignment is in the appendix of the book. It's going to talk about, I told you before, the spectrometer and how it works. What is being measured when we use the spectrometer. Then on Monday in our lab, we'll use the spectrometer. I'll have one out for you to see tomorrow, and we'll talk about it. They're very simple to use, and they give us very good results. It'll be good. This is where we're going to start to get into the kind of the nebulous part that there's nothing already in your brain to attach this to, so we're going to have to kind of create a new little synapse in your brain, okay? That's this part, the order. The order of a reactant, when you have, let's say I don't have a chemical equation out here. I'll have one on the next page. We're going to have to try to determine the order. The order of a reactant, every reactant in a reaction has an order. The order of it describes how much its concentration affects the rate. The order does not determine how fast the reaction goes, and that's what people tend to mix up. There's going to be three main orders that we deal with. There's zero order, first order, and second order. That's pretty simple, zero, first, and second. If you have a reactant that's zero order, that means its concentration doesn't affect the rate. You could double its concentration, the rate's still going to be the same. Zero order. If it's a first order reactant, that means that its concentration affects the rate to the first power. So that means if you double the concentration, the rate of the reaction is going to double. It's a first order relationship, first power relationship. If you have a second order reactant, that means that reactant, its concentration affects the rate to the second power. So if you double the concentration of the reactant, the rate quadruples. That doesn't mean, if you have a second order reactant, that does not mean anything about how fast the reaction goes. It just determines how much the concentration is going to affect the rate. It's kind of strange. So anyway, I'll have said that, and then we'll talk more about it. Let's see. Don't write anything down about this slide. It's just redundant. I'm going to go on to this one. We're going to look at first the integrated rate law. Remember, there's the integrated and the differential rate law. I gave them actually in the reverse order before, but we're going to do the integrated rate law first. Our lab that we do on Monday, we're going to have a reaction, try to determine the integrated rate law of the reaction. So in this reaction, we have a decomposition. I have just taken this out of I don't remember if this is out of the Zumdahl book or some other source, because I've used this now for a number of years. And there's no good reason for me to use this, I guess, except for all these things are gases. The reactants and the products are gases. I've never done this reaction myself. I don't even think I've ever dealt with N2O5 in my life. Honestly, I don't even know if it exists. It probably does, I guess, if it was in the book somewhere. But we have found, now, where it says experiment shows this is a first order reaction, you are not required to know how we got that. I'm just telling you that it is found that this reactant is first order. So just take that as a given. Okay? Here's what we do with it. If it's first order, that means this. Remember, the N2O5 is the reactant. So negative change in the reactant concentration over time equals K times the reactant concentration to the first power. What do you see on the left side of the equation? Have you seen this already today?
It's the A.
Yeah, it's like the A that we saw on the first couple of slides. This represents the rate of the reaction. It's the change in the concentration over time, the rate of the reaction. And the rate of the reaction is equal to, see that letter K? Don't miss that K. The K is called the rate constant. Every reaction has its own rate constant. This K value is what tells you how fast the reaction is. If K is high, it's a fast reaction, makes product quickly. If K is a small value, it's a slow, dreadful reaction, it takes forever. Okay? Now, the N2O5 to the first power, all that says is that is how much the concentration of N2O5 affects the rate. And like I said, if it's a first order reaction, that means that if we double this concentration, then the rate is going to double. If it were a zero order, if that was zero, stop. If that was zero, that would mean that if we double the concentration, the rate would still be the same. Because it would be 2 to the 0 power, which would still be 1. The rate would not change if it was a zero order. All right, so here's what I'm going to do now. I'm going to bring in the calculus part of this. If you've never seen integration before, it's going to look like a foreign language or something. You're going to be like, what? But don't worry about it. Seriously. The only reason I do this is for the benefit of the people that have gotten that far in math, you can see how we get these equations, okay? The rest of you, it'll just give you something to look forward to. How many people have had calc and have done integration? A few of you? Just like, not that many?
Like, had it?
You're doing it. Some people said they're doing it right now in their classes. Okay, okay. So yeah, it's going. I'm going to extend the page some and make this a little bit, give myself more room. So this is the rate. This thing is the same thing as that. Now what I did was I'm looking at a time interval, and when I change the delta to the d, that means that at any point we can look at the very small time change in what's happening to the concentration. We're going to put the N2O5 terms all on one side. We have a change in N2O5 there and an N2O5 concentration there. We're going to move them over to one side, everything else on the other. So, including that negative sign, I'm going to push it over to that side. So I'm going to multiply both sides by negative dt, and it's going to cancel there, and that negative is going to cancel, and that's going to cancel. It's going to be over there. And I'm also going to divide out the N2O5. So it's going to look like this. D of N2O5 over N2O5 equals negative k dt. So t is the x-axis, it's the independent variable. This says over a certain time interval. So we're watching this reaction as it goes on over some time interval. And this is where we're going to integrate from 0 to time t. All right, so once you integrate that side, we also have to integrate that side.
What is that?
That's what I mean. Just smile and shake your head like, oh, okay.
So great.
Because once again, I'm just showing the people that have done calculus how we get the integrated rate law. The rest of you just have to trust that it's right. Okay. Now, this is the same thing as the integral of 1 over N2O5 concentration, d N2O5, all right. Now, over there on the left, I had d N2O5 over N2O5. Down here, I just made 1 over N2O5 times d of N2O5. Would you agree that that is the same as that? Yeah, this is just multiplying and dividing. It's order of operations. It doesn't matter which order you do them in. Down here, I'm just choosing to divide before I multiply the numerator. It's fine. Why did I write it like this? Okay, my calculus friends, what is the integral of 1 over x? ln of x, that's right. The natural log of x. All right then, see? Now you know that ln of x turns out to be the integral of 1 over x. Okay, so here's what it means. This is over a time interval, so it's ln of x at some time t, not of x, it's ln of N2O5 at time t minus, this is going to be a big stinking mess. I should be able to write over there, but I can't write over there unless I maybe did. That just makes it all big, and I still can't fit anything in. I feel so stupid when I use it. It's called a smart board, but it's none of that.
Yeah, but the board is smart.
I know, Amber. I don't need to be reminded of that. All right, so you've got me. So down here, this is over a time interval. It's ln of N2O5 at time t minus ln of N2O5. I'm still going to run out of room. At time 0 equals. And what is the right side? How does that evaluate out? Negative kt is it? Yeah. It would be negative kt minus negative k times 0. So we just leave that 0 part out. It's just equal to negative kt. Yep. What did we just do? Right, well, I'll tell you what we just did. Remember, you were given, in this little microscopic print,